All right, so this is something I figured out today that I think is pretty cool. So here's a graph of y equals 1 over x. And I've shaded in that area from 2 to 4. And it's about 0.69. Right? And now I'm going to move that left endpoint down to 4. But I'm going to move the right endpoint all the way out to 8. And I want that right endpoint to be double the left endpoint. That area is exactly the same. Right? Believe me, the computer actually is computing this number here. And I can put this wherever I want. I could go from 3 to 6. That area is still going to be the same. In fact, I could go the area from 10 to 20, that tiny, tiny, tiny sliver, that area is still equal to 0.69. So what is going on? What is that number? Well, that number is the natural log of 2. And so I'm going to show you why that's going to be the case. Right? So first of all, what is the natural log of 2? Well, we defined in another video, we defined natural log to be the area under the graph from 1 up to that number. So this blue area right here, that is representative of, that area is equal to the natural log of 2. And so what I've got to try and convince you of is I've got to try and convince you that no matter where this thing starts, let's say we go from 4 to 8, that this green area has the same area as that blue area. That's kind of cool. Or maybe if it's down here, I have to convince you that this area has the same area. Or that this area has the same area as the blue area. So how am I going to do that? Well, let's leave it there. So what I'm going to do is I'm going to do this animation thing. And so I'm going to turn off this area. I'm going to shade it in. Let's have it be purple. And what I'm going to do is first I'm going to shrink everything. I'm going to divide all the coordinates eventually by 3. So I'm going to take this coordinate here is 3, it's going to go down to 1. And the 6 is going to go down to 2. So I'm going to scale everything down. It's going to make it a little bit slowly. But what I did was I'm just scaling the x coordinates. So when it's done, I have everything. It's exactly that same thing, except in the x direction it's been scrunched. So the height is still the same. The height is 0.3. That was the height over here. I think we started at 3. So the height's going to be the same. And so what I did was I scaled down by a factor of 3. And, well, obviously my area got smaller because I did that shrinking. But now if I undo that by increasing the y direction, if I scale everything by a factor of 3 in this direction, look at what happens. Once I get to 3, I wind up there. And so what's happened is I've shown, I can kind of undo this if you want. If I undo this property, I've shown that this purple region, after I do those 2 transformations, is going to wind up turning into that blue region. Now, why should the area be the same? Well, I scaled one down by a factor of 3 and the other up by a factor of 3, so maybe that convinces you. If not, let's just see what happens when we do the same animation, but just with the unit square. So here's a unit square. First, let's scale it down by a factor of 3. You see it's going to make it smaller. And then now let's scale it up by a factor of 3. And so what we've actually done is we've applied what's called a linear transformation to the plane. And because we've scaled one by a factor of 3 and the other by a factor of 1/3, the area is going to be preserved. And so this is a pretty cool animation, I think. I'm pretty excited to figure this out. I figured it out while I went on a walk today. And what's cool about this animation is it works no matter what you use. So let's just do one more. Let's go from, let's go from 6 to 12. That tiny, tiny, tiny little area. First, let's scale in the x direction. And then let's scale in the y direction. It's just beautiful, I think, how that worked out. And I never knew that until today. So this is something that's new to me and now can be new to you. Thanks for watching.